Hello, my name's Dr. Fogarty, and I'm going to talk today about equilibrium. So far in class, we talked about mainly what I'd like to call one-way reactions. So for instance, we have the combustion of methane in oxygen. Where our methane burns to form water and carbon dioxide. Now, this is a one-way reaction because when we react methane and oxygen, all of the atoms involved in the reaction, if we have good mixing and everything else is nice, all of these atoms will end up as products. 100% of our stuff ends up as products, and 0% of our stuff sticks around as reactants, okay? This is a one-way street. You form 100% products from this reaction. In chemistry, we have other types of reactions. We have two-way reactions or equilibrium reactions. For instance, a common test for the detection of the iron 3+ ion is to add thiocyanate ion. And I'm just drawing the net ionic reaction in this case. And this is a two-way reaction, and it forms a complex ion, which is iron thiocyanate, and that ion has an overall charge of 2+. Now, we can see that the source of its charge from 3+ iron minus 1 thiocyanate forms a 2+ iron thiocyanate complex ion. This iron thiocyanate complex ion has a red color. In this reaction, we can go two directions. In other words, we can have iron and thiocyanate react to form our complex ion, but our complex ion can also break apart and go back towards the reactant side. And this can happen all the time, okay? So let's think about an experiment. What we can do is we can take a test tube of iron 3+ and a test tube of our thiocyanate ion and dump it together. When we first dump them together, 100% of our stuff is in the reactants. When we dump them together, they will start reacting to form our complex ion, and we'll begin to notice a bit of a red color to appear in our test tube. Over time, the red color will get darker as more and more of this forms. But as more and more of this forms, it will begin to also fall apart and reform our iron 3+ and our thiocyanate. So what we get is a kind of cyclic reaction where we're forming product and we're breaking up product, and we're forming product and we're breaking up product, okay? Over time, eventually, this red color will only get to a certain amount of darkness. In other words, we'll kind of reach a stopping point for the reaction, at least to our eye. On the atomic level, we still have things being created and destroyed all the time. But on the macroscopic, scientific level, we have seen our reaction has reached equilibrium. This state, dynamic equilibrium, is reached when the rate of our forward reaction equals the rate of the reverse. And so what we have is this dynamic, because we're constantly forming products and breaking up products to form reactants. Things are going in a cycle. Things are continually moving at the atomic level. But because the rate of the forward reaction is the same as the rate of the backwards reaction, we have reached a kind of stable point, and our test tube only gets so red. Okay? So, how do we account for this as chemists? Well, one way to account for equilibrium, to know how much product we have formed and how much reactants are left over, is to use an equilibrium constant expression. Okay, so we have an equilibrium constant, KEQ, which is the ratio of the products over the reactants. And we use, for an aqueous system, the concentrations of our respective species. So in other words, we would rewrite this equation as our iron thiocyanate 2+ ion concentration over our iron 3+ concentration times our thiocyanate concentration. And here I have used the convention where our square brackets mean concentration, and that is in moles over liters, which is also our big M that we learned about when we talked about dissolving species. Now, we have this ratio, okay? And if we measure the concentration of each of these species, we'll get out a constant if the system is at dynamic equilibrium. What is the number for this system? It is 138. Now, what does this tell us? Well, the 138 tells us that there's roughly 138 times more stuff on the product side than there is on the reactant side. So we have an equilibrium, we have a balance between our reactants and our products, but the balance is shifted towards the product side. So that is how we address equilibrium in solution. Let's look at a gaseous system. So an example of a gaseous reaction that has an equilibrium is the dissociation of dinitrogen tetroxide to form nitrogen dioxide. And nitrogen dioxide is what makes pollution brown. It is a brown gas, okay? So how do we make our equilibrium expression for this reaction, especially considering we have a stoichiometric number right there, a 2 in front of our NO2, okay? The way we write the equilibrium expression for this reaction is Kp. This symbolizes that we're dealing with gases, and we use the pressures of the gases rather than our concentrations. And because there is a stoichiometric number of 2 there, we square the pressure of our NO2, and that is over the pressure of our reactants, which is our dinitrogen tetroxide. In general, we can write a general form for the equilibrium expression. If we have a reaction where we have stoichiometric numbers in front of various products and we are in equilibrium, our equilibrium constant expression will be, and I'm writing this for aqueous solution, where we have the concentration of all of our species raised to the power of their stoichiometric number. And that is what we'd like to cover in this brief introduction to equilibrium. Thank you very much. Bye.